Okay, we're back. When I ran dmessage a little bit at the beginning of, or at the end here of part one, um, I should have done it with this following command, but let me welcome you again to, let me get Mr. Cheese here. Okay, let me welcome you to part two of week 8 of cis204, Unix shell scripting and utilities, and I'm going to kill the cheese. Okay, there we go. Let me do this. Let's do this dmessage, and we'll do the -- human, and we'll pipe that to less. Now, of course, if I see a -- command, that means it's a POSIX version of the POSIX option. So there we go. How is that any much more human readable than what I already had in dmessage? Well, not much. Anyhow, this is what dmessage shows you. It shows you what's going on at boot. It can be useful if you intend to do system administration. So let me get out of that. Oh, look, I am not root anymore. Good. So let's go forward a bit. So the init, which is that initial program that runs, there is a new thing called Upstart. That's an init replacement for the traditional Unix 5 init. Upstart's written with the NIH utility library, libNIH, and this is a small, efficient, safe library. Safe being it's relatively immune to hacking. Library of generic routines. It's designed for applications that run early in the boot sequence. In other words, it's a plumbing structure. It's a series of pipes. Reliability and safety is critically important for an init daemon since it has to run as super user, and it's responsible for managing critical system resources. And then if for any reason the init exits, the machine panics, basically. The kernel panics, and you're left sitting there going, what do I do now? The run levels, yes, there are 6, or actually 7. So 0, and this is Red Hat and CentOS, 0 is halt, 1, run level 1, is single user text mode. And let me do this. Even though this is an Ubuntu environment, let me cd to etc rc.d. Yep, cd to etc. cd to /etc. There we go. Let's clean this up and let's see what we've got here. I think I've got an RC. Ah, there they are. So you can see there's an rco.d, there's an rc1.d. So if I do cd to rc1.d, these are the things that can come up in 1. Now, we'll come back to this in just a moment, but notice that every one of the files in this ls-l, they all point to somewhere else. These are all logical links to something else, but every one of these links has either a K or an S at the beginning, with the exception of the README file. So if we do this, it says the scripts in this directory are executed each time the system enters this run level, which is run level 1. The scripts are all symbolic links whose targets are located in etc init.d. Generally, it is not necessary to alter the scripts in this directory. Their purpose is to stop all services and thus to put the system into single user mode. So the K's and the S's, we'll come back to those. So single user mode 1. There's a user mode 2, not defined, not used, but the user could define it. 3 is a full multi-user text mode, not GUI, text mode. 4, it's not used. You could define it if you wanted to use it. 5 is the full multi-user graphical mode with some sort of an X-based login screen. Run level 6 is the actual reboot of the machine. Not a halt, but a reboot. Shutdown is take it to run level 0. If I were to issue the shutdown command, what would happen is I would start working on the scripts that are in rc0.d. And there they are. Notice what I don't have in the rc0.d. I have no script, this logical link, that has an S in front of it. They're all K's. How come? Well, the S's are starts, the K's are kills. When I want to power the system down, halt the system, I need to kill all of these extra utilities. So this also utils, which is the also utils are the sound card, Bluetooth needs to come down, the CGM, which is part of the screen manager, the CG proxy, CUPS browse, the IRQ has to come down, kernel ops has to come down, the light DM, which is part of the GUI environment, the logical volume manager needs to come down, MySQL comes down. You can see all of this stuff needs to be taken down, and actually it needs to be taken down gracefully. Let's see, let's do an LSL on K01NM. And let's do this. More /init.d/nmdb. So, hey, what is that? It's a shell. Interesting. Aren't we working on shells? Okay. So I've got the shebang line, which is the # ballbat /bin/shell. So this runs under the born shell, not the born again shell, the born shell. Then some comments. It provides the NMDB, the required start, the network, the local FS, and what's that $ in front mean? Those are variables that are required to start and required to stop. The X start before SMBD, which is SMBD, and you're looking at NMBD here. Short description, start the Samba NetBIOS name server. Then it sets a couple of variables. It clears conflicting settings from the environment. It unsets that temp dir variable. See if the daemons are there. Test -x to see if they're executable. That user sbin NMDB. Or exit. If they're not there, exit. So there we go. We've seen all this before. And then it asks you to source the lib lsb and net- functions. So you can see this is basically some of the stuff that we've been going through. And it's sitting there in your systems when you're using them. The scripts are there. They're in the background. You don't see them, but they were built by people that needed to make this system work. So there we go. So how do we know where we're at? Well, I know we can print working directory, but what run level are we at? Let's get this cleaned up, and we do a who-r, right? Run level 5. That makes sense because we're sitting in a GUI right now, aren't we? Okay. Now let's move forward here. Inodes. And I'm going to pause for just a moment, and we'll come back and do inodes. Okay. I'm back, I think, after having taken a drink of water. Now we can talk about inodes. So in the grand scheme of things, when you create a directory and then put a file in the directory, what are you actually looking at when you do an ls and you see the directory and you see the file name? You're actually seeing information that's delivered from the inode. You're not seeing the actual file. You're not seeing the actual directory. You're seeing the pointers to the file and to the directory. So what is an inode? An inode is an index node. It has a directory entry. There's a name and an index node. The index node contains information about when it was accessed, when it was modified, and when it was created. It has a size of the file. It has the user ID that owns the file. It has the group ID that owns the file. It has the permissions. It also has pointers to where the file, the data in the file, is actually stored. Block 1 contains file content. Block 2 contains file content. These blocks will be whatever the physical size blocks that the system says you've got to have. So if I've got a 200 byte Word document, it will be contained in my machine in a 4096 byte block, in other words a 4K block. So my 200 bytes of text is stored in one 4K block. That means that the index node for that file will have a pointer to one block and one block only. Block 2, 3, 4, 5, 6, 7, 8, 9, and 10 aren't needed. It is using up only 200 bytes of 4,000 possible bytes. So you can see little files tend to tie up a lot of disk space, more so than you would think. Wait a minute, that file's only 200 bytes long, but it takes a 4K block to house it. You can't break the block down any further. Now, if you were designing a system from scratch, you'd want to take into account file sizes to determine how you were going to physically lay the logical piece of the system out. So, moving forward, once you fill up X number of blocks, there's a pointer to another set of block addresses. That's an indirect block. With 64-bit OS, I think it's 64-bit OS, we've got 3 levels of indirection that you can get to. So I can go to a block address that points to block addresses that points to block addresses that then point to actual blocks. So the inode is information about the file. It's information about when the file was created, when the file was modified, when it was last accessed. It has information about its size, it has information about who owns it, what group owns it, and where the physical file actually is. It has pointers to where the physical file actually is. And that file could be scattered throughout a set of disk drives. And even more fun, that file does not have to be in a contiguous location. Although it's better if it is, it does not have to be. It can be fragmented. So here's that level of indirection that we talked about. An indirect block, a double indirect block, and a triple indirect block. So an indirect block will point to a list of addresses. This will point to a list of data blocks. There will be 10 addresses stored in this direct block. It will point to individual data blocks. So these point to individual data blocks. There's a list of 10 direct block addresses. This points to a list of 10 of these 10 direct address blocks. Each one of those points to a data block. This goes to a indirect block that points to a direct block that points to a data block. This points to a double indirect block which points to a single indirect block which points to a direct block which points to data blocks. So you can see you can get very large file sizes that way. It used to be that the max file size was right around 2 gigabytes. That's not the case anymore. So, file system type. Well, we've heard of FATs and FAT32 and NTFS, and if you're in the Microsoft end of the business, then that's what you're used to, is the NTFS. Linux has an ext4 partition, and on this machine I'm using a Linux device mapper. It has the Ubuntu VG root. It has a logical size of 512 bytes, and the physical size, the actual physical block size, is 4K. The partition table is a loop. It's partition 1, starts at 0 bytes, ends at 500 gigabytes basically. And it is an ext4 file system. So what does that mean? Let's go here and see. ext4 file system. See what it has to tell us. So, it's a fourth extended file system. It's a journaling file system for Linux. And the fact that it's a journaling file system means that it keeps track of what it's doing. That allows it to, in case you and I both decide to write to the same file at the same time, it tries to keep that from causing problems, basically. So, backward compatibility. It's backward compatible with ext3 and ext2. ext4 can pre-allocate on disk space for a file. It can also delay allocation. A directory can have at most 32,000 subdirectories. If you get to that many, you're having fun beyond belief. And here's the bit about journaling. The ext4 uses checksums in the journal to improve reliability. Since the journal is one of the most used files on the disk, the journal basically keeps track of what's being written when and who is writing it. So, improve timestamps, and then you can get some more information on this. So, let's go back to this. Okay. So ext4 divides a storage device into an array of logical blocks, both to reduce bookkeeping overhead and to increase throughput by forcing larger transfer sizes. If you're transferring small files, then okay. So an ext4 file system is split into a series of block groups. You reduce the performance difficulties due to fragmentation. The block allocator tries very hard to keep each file's blocks within the same group. And that helps when you're seeking information on the disk, because the less you have to move the disk heads, the faster you get the information back to the program. And remember, we talked about timing early on in this process. If it takes minutes to go on a bus from memory to the CPU, it takes decades of time to go from a file system to memory to the CPU. So the less fragmentation you have, the quicker things run. ext4 file system can support file sizes up to 1 exabyte, and files with sizes, single files with sizes up to 16 tebibytes, TIB. And you're on your own for looking up that stuff. Okay. So let's do this. Let's look at some inodes. I'm going to cd to my home directory. cd tilde or cd. And then I'm going to do an ls-laki. L-A-H-K-I. Okay? Yeah, interesting. So what have I got here? That's all this wonderful information. Long listing. A gives me the hidden files. The H gives me the human readable file size. The K, I'm going to have to think about that one for a minute. But the I is the inode. And that's what we're seeing here at the front of this. So if I do an LSLI, I get that. If I do an LS-LK, I get that. If I do an LS-LH, I get size in human readable format. Okay. So let me do this. Let's do a df-ih. udev. Look, it tells me how many inodes are available. See, the inodes are allocated just like a file would have space allocated for it. So there are inodes available to the device. I have 29 megabytes of inodes available under the root. In other words, my big file system. It shows me how many inodes are used, and it shows me how many inodes are free. And it gives me a percent of use of the inodes. there is a limit to the number of inodes that are available on a system. So you can also run this stat, give it a file name, and you want to do a pwd just to make sure you're in your home directory, and you can do that. So I'll let you do that on your own. We're going to come back to this one in just a moment. This is, well, actually, we'll go through it now. So let me do this. I am on my home directory. Let me make sure that I'm there, right? Okay. And I'm going to touch this. Touch AB splat single quote, right? So what am I actually creating? I'm creating a file that has a double quote AB and a splat in it. There it is. So how do I remove that? Well, let me do this. Let me do that. LSIA. There it is. Okay. Let me copy that. Remember we used the find command earlier? And we told it name? Let's try this. Find dot minus inum. Control V. Let me paste it. Here we go. Paste that in there. There's the inum. Hey, I can actually run a command from the find command? You betcha. rm-i, put the curly braces, give it this escape, and hope it comes back and does it. And yes, I do want to remove that thing. Is it there? No, it's gone. Okay. So that was kind of fun. Now we're going to jump into useful utilities in part 3. So I'll see you in just a moment.